Welcome to the lecture series on hydrogeology. So in this lecture, what we are now going to discuss about the porosity. Porosity is the percentage of void spaces in a rock. So this is the exact definition in a nutshell. Rather very simply, if you want to understand, it is nothing but the open spaces available in a rock or the void spaces present in the rock. So porosity is nothing but the open spaces. You see the diagram. So this is the open spaces. This open spaces is called as porosity. The open spaces will vary, depends on the size of the particles arranged in such a way. As a geologist, we know that there are many criteria of the arrangement. The gravel size or the packing material or the cementing material. It all controls the amount of open spaces in a particular rock. So in a nutshell, if you want to understand, it is nothing but it is a open spaces. So this is normally defined, it is with respect to the ratio of volume of open spaces to the total volume of the rock. So this is the exact definition. This also can be defined as the ratio of the volume of the voids or the open spaces or pore spaces divided by the total volume. Open spaces divided by the total volume. So this is the formula for the porosity, always represented as meta V pore spaces to the V total. Porosity depends on size of the sediments, shape of the sediments, and sorting of the sediments. So this is the best diagram for you to understand that this is large openings are there. You can find the packing material in between. You have the large openings. So these large openings are called as high porosity large spaces. If the large openings in between, if you have the other grain sizes, like this is bigger in size and medium in size and small in size, suppose if it is arranged in between, the open spaces will be reduced parallelly and cause the low porosity, and the total volume of open spaces in that particular area is very less. So this is visualization that how you are assume that your water is now traveling in the pore spaces. So this is the sediments, and in between the sediments you can find the pore spaces. The pore spaces are filled with the water. So this is the typical examples of mineral grains and water in the pore spaces. The best examples are sandstone. This diagram represents relatively larger pore spaces between mineral grains and sandstone. It is very large. And this is the second diagram. You can find the minerals, mineral grains, but it's fully packed. You can find only the small openings between the grains are filled with the water. The grains, the pore spaces has to be connected with each other, otherwise water will not move from one pore spaces to another pore space. That's called permeability. That is the discussion of the next topic. So in a typical crystalline terrain, you will be able to get your openings like this, and in typical sedimentary formations like sandstone, you will be able to get your open spaces in the subsurface like this. Here it is a relatively very small pore spaces, and here it is very relatively higher pore spaces. Material can be porous without being permeable, but it cannot be permeable without porous. If you have open spaces, then you can think of whether the open spaces are connected or not. If you don't have open spaces, then there is no question of permeability. That is the you can find the porous but not permeable. You can see here the material is not allowing the water or the air from one place to another place. It is packed. So it is porous but not permeable. It is porous, you can see it's permeable. So groundwater can be found in pores between grains, primary porosity, as well as in fractures. That after the formation of the pore spaces or the open spaces called secondary porosity, when during the formation or the origin of the rock, by the time if there is openings, that is called primary porosity. Normally this will be there in the sedimentary rock, and secondary porosity will be there in the metamorphic and crystalline igneous formations. What are the different factors? As I said, size, shape of the sediments. So this is the examples of your porosity, how the shape and size is going to affect. The well-rounded particles will have in a soil and rock will have normally more porosity. If the shape of the particle is well-rounded and arranged in such a way, then you will be able to get higher groundwater, sorry, high open spaces or high porosity. If it is irregular, the porosity will be reduced. So that is the examples. That this is the packing. If it is regularly packed, you will be coming to the size distribution. If all particles are the same size, then possibilities of higher porosity will be there. Particles are same, shapes are same, round packing. If it is regular packing, higher groundwater, I mean higher porosity. If it is arranged in an inclined way, the porosity will be parallelly reduced. If the sorting is uniform, it will be having higher porosity. If the sorting is ununiform, it means from small size particles to the larger size particle will affect the openings in a particular rock. That is, you will be able to get your low porosity. If the shape, grind shape, if it is bigger in size, and you'll be having higher porosity. If the shape is very thin and if it is arranged like laminar sediments, then automatically the open spaces in a particular rock will be reduced and leads to low porosity. What is the relationship between the packing and porosity? As I said in the last figure, if it is regularly arranged, this is called cubic packing. If it is a cubic packing, the porosity, it is scientifically calculated that it is 48%. The same material is arranged in a rhombohedral shape that we have studied in calcite. If it is arranged in a rhombohedral shape, there your porosity will be parallelly reduced and you will be able to get your porosity of 26%. If the open spaces are reduced, what does it mean? It means the amount of water stayed, I mean, placed in the particular rock also will be reduced, and then the expectation of the water in a particular rock also will be parallelly reduced. So here the porosity is high, here the porosity is low. Here this is controlled by the arrangement of sediments. And this table shows the porosity ranges of sediments. If it is well sorted sand and gravel, the porosity will be between 25 to 50%. Sand gravel mixed, the porosity will be reduced down to 15%, that is between 20 and 35. If it is a glacial till, the porosity is 10 to 20%. In silt, it is between 35 to 50%. In clay, it is between 33 to 60%. And you have your grain size here, and you have the pore spaces here in the sediments, and in your crystalline rock where you will get your void spaces, and there will be a small crack leads to this place to save water. And this is the best examples of moderate porosity and high permeability of larger grains, and high porosity and low permeability in the clay formations. So this is sedimentary clay. Clay will be normally clay is higher porosity but less permeable. Pore spaces are not connected each other, whereas in sediments it is moderate porosity and high permeability. Porosity of sedimentary rocks. Sedimentary rocks are formed from sediments, as we know, through the process called diagenesis. The primary structures of sediments are preserved in the sedimentary rock. Normally, primary porosity will be there in the sedimentary rock. The porosity of a sandstone is influenced by the grain size, size sorting, grain shape, and the cementing media of the original sediment, fabric of the original sediment. Bedding planes may have primary porosity formed during the deposition of sediments, and secondary porosity if the rock has moved along the bedding plane. So this is the porosity percentage with respect to sandstone up to 49 from 14, and siltstone 21-41%, claystone between 41 to 45%. Openings are more but not interconnected with each other. Shale is between 1 to 10 and limestone is between 7 and 56. Dolomite is between 1933 and moraine is between 25 and 40. The pore spaces in the larger grains and pore spaces in the smaller grains. Porosity in plutonic, I mean metamorphic rock, those formed by intrusive igneous process. Examples of these rock types are called, as we know, granite is distributed much, and metamorphic rocks are formed, as we know, because of the heat and pressure and pre-existing rock. Normally we get after the process of this heat and pressure, that's we'll be able to get schist and gneiss. Generally both these rocks normally it is having very low porosity as they are formed by interlocking crystals. Two geological process after this formation, maybe a weathering and fracturing leads increasing the pore spaces. Rock in a fault shear zone may be extensively fractured. Fracturing increases porosity of crystalline rocks by about 2 to 5%. Weathered plutonic and metamorphic rocks can have porosities in the range of 30 and 60. Porosity on the near surface rocks like volcanic rock, those formed by the extrusive igneous activity, similar in chemical composition as well as if it's having with plutonic formation. Porosity of basalt is normally between 1 and 12. Porosity of pumice is very high. It's a glassy rock, have porosity of more than 87%, but not connected with each other. Values of porosity of tuff is ranging between 14 and 40. Recent volcanic ash may have porosity of 50%. Weathering of volcanic deposits can increase the porosity values up to 60. This is the percent porosity with respect to various rock types like volcanic. This is solid rock and this is unconsolidated rock. In solid rock, so this scale is given 0, 10, 20, 30, 40, 50. So this is the range of porosity. In unfractured rock, the porosity is less, and fractured rock, it may go up to 50%. Similarly, unfractured intrusive igneous and metamorphic rocks will go up to 7%, and then if it is more fractured, it will go sometimes up to 10%. Similarly, for limestone, because of the dissolution process, because when water interacts, it may go up to 50%. Limestone with cavernous opening, it goes up to 20%. Mudstone up to 30%. Sandstone up to 30% with poorly sorted less and well sorted like little cement. If you add, what will happen? The porosity will increase. Conglomerate is between 10 to 30. Glacial till between 10 and 20. Silt and clay between 37 to 70, and similarly for sand is between 30 and 50, and gravel is between 23 and 40. So this is the percent porosity representation of the graph. This the lecture part is over with respect to porosity is concerned. We will see in the next lecture. Thank you very much.